Okay. Thanks, Doris. I think I'll just start over and stop the recording. So welcome to today's SAM webinar. We're going to talk about front-of-meter systems, modeling front-of-meter battery systems in SAM. My name is Paul Gilman. And this is the last in our series of battery webinars for 2020. We have one more webinar coming up in October on PySAM. You can register for that workshop on the events page on the SAM website, and you can also find recordings of these other webinars on that events page. And you can find recordings of older webinars on the topic pages at sam.nrel.gov. If you have a question today, please use the questions box to type it, and one of my colleagues will answer it either by typing or stop me to answer it as I'm presenting. We'll also have a Q&A session at the end, so we may hold off answering your question until the end, or you could wait until that time to type your question. So I'm going to start with a quick introduction to SAM and then talk about front-of-meter batteries. And then we'll have a few examples of modeling front-of-meter storage in SAM. And as I mentioned, a Q&A session at the end. So SAM is the System Advisor Model. It's free software developed by the National Renewable Energy Laboratory, mostly with funding from the Department of Energy, but also from other partners. And SAM fundamentally does two things. It has a performance model that calculates a power system's energy output over 1 year. That could be on an hourly or sub-hourly basis. It then feeds that power generation profile into a cash flow model, which calculates the project's costs and benefits over a multi-year period to calculate metrics like net present value and levelized cost of energy. You can check out the Intro to SAM webinar that's on the SAM website for more general information about SAM. So front-of-meter battery systems are battery systems that are installed as part of a power generation project. For example, the one that we see here has a PV array with battery storage. You see the batteries in the foreground. Or it could be a standalone storage project, but it's characterized by earning revenue through power sales. And that might be at a power price that's agreed to through a PPA or a power purchase agreement, or it might be market prices for a merchant plant project. And generally what you're trying to do is determine whether a project is profitable given its installation and operating costs and the amount of energy that it generates. So these are some of the considerations for a front-of-meter storage project. You want to charge and discharge the battery in such a way to maximize the value of the generated power, and you want to minimize the cost of the project, of course. You want to take into account the cost of replacing the battery based on its degradation over time. And you also want to respond to the generation profiles of the solar array if it's connected to a PV system or perhaps a wind system. And also you want to consider the variations in pricing. And then there may be some external constraints. There may be policy requirements, for example, that a certain percentage of the energy used to charge the battery comes from a renewable energy source, such as the ITC requirements, or there may be interconnection limits that affect how you operate your battery. So SAM's battery storage model comes coupled with either the detailed PV or the generic system model. And the generic system model can be used to model different kinds of projects. So if you're modeling a wind project, for example, you could use a wind generation profile from the wind model and import it into the generic system model to use to model it with a battery. We also have a simple PV watts battery, which I won't be discussing here, but is covered in other webinars. And it's the financial model over on the right side here that determines whether it's a front of meter or behind the meter storage system. So the front of meter would be any of these power purchase agreement options, single owner or partnership models, or the merchant plant financial model. I'm going to use the single owner model for most of the examples here, but the battery modeling portion of the project would be the same for any of these other PPA or merchant plant options. And then of course the behind the meter model, we have a whole webinar on that was given a couple weeks ago. That would be for any of these distributed financial models. So we're going to look at a PV storage system to start with. And the design steps for a PV system are generally, first you choose a weather file, which depends on the location of the project. And then you design and size the PV system. And then you would design and size the battery system, choose dispatch options and lifetime options, and then define costs. So I'm just gonna focus on the dispatch options here because all these other design steps are covered in detail in other webinars, and I provided the links here so you can find those. So we're gonna focus on the battery dispatch options for front of meter storage. So because of that, we're gonna use default inputs for most of the inputs that in the cases that I'm demonstrating today, except for battery sizing. We'll play around with the size of the battery and whether it's DC or AC connected, and then of course the dispatch options. And again, you can find information about the other battery inputs on the battery videos page of the SAM website. Okay, so we'll start with manual dispatch. So the manual dispatch option in SAM allows you to define when the battery charges and when it discharges, and whether it charges from the system or from the grid. And to do that, you define up to 6 dispatch periods, and each period it would be either a charge period or a discharge period or some combination thereof. And then you assign each period a time in the schedule matrices down here. And a thing to keep in mind here is that the charge and discharge pattern that you set up here is going to determine how the battery is cycled. So it'll affect battery replacements, not just how the battery is charged or discharged. So let's switch over to SAM and have a look at a file here that I've set up for this demonstration. So this file has 2 cases, and I'll show you how to create cases later, but we'll just start with this pre-set up file. It has a PV case, so this is photovoltaic single owner, and it has a PV battery case, so PV battery single owner. And the PV system is for a project in Phoenix. If we go to the system design page, we can see it's a 20 megawatt project, has a DC AC ratio of about 1.2. And it has a 7 cent per kilowatt hour PPA price and an installed cost of about $1.07 per watt with a $13 per kilowatt annual operating cost. So if we run a simulation for this PV only system, we can see here that the net present value is $600,000, so it's positive. It has an internal rate of return of 7.85%, so we could consider this to be a reasonably profitable project. Now let's take a look at the PV battery case. This is for the same PV system, so it's in Phoenix. It's 20 megawatts array capacity with 1.18 DC-AC ratio. But it also has a battery, So we have a new battery storage page. And the battery here is a 4 kilowatt hour battery with a maximum discharge rate of 1,000 kilowatts. So we'd consider that a 4-hour battery. For 4,000 kilowatt hours divided by 1,000 kilowatts is 4 hours. That's indicated here at this time at maximum power calculated value. And we've chosen the manual dispatch option. So we have a simple dispatch schedule set up here. It just has 2 periods. Period 1 is the battery is allowed to charge from the system. And period 2, the battery is allowed to discharge at 25% of its available capacity. So it won't fully discharge in that hour. It'll discharge up to 25% of its available capacity. And we just have the 2 periods are from midnight to 3 p.m. Same for the weekday and weekend. And we can discharge the battery from 4 p.m. to 11 p.m. Throughout the year. So just a simple dispatch schedule. And we have the same PV system cost. We have an additional battery cost. So the battery cost here is $200 per kilowatt hour of installed capacity plus $600 per kilowatt of installed capacity. So that's for a total installed battery cost of $1.4 million. And we have an additional operating cost down here, the battery replacement cost. So whenever SAM determines that the battery needs to be replaced, a $500 per kilowatt hour of battery capacity cost will go into the cash flow. So let's run a simulation and see what adding a battery did to our net present value. So here we have a very negative net present value of $3 million. So our battery seems to have increased the cost of the system without increasing the revenue enough to cover that cost. We can explore this in a little more detail by looking at the cash flow graph down here. So this after-tax cash flows is the cash flow that this net present value is calculated from. And we can see our initial cost in year 0. And we have accelerated depreciation. So that's a benefit to the project in the first 5 years. This has a 18-year debt period that's defined on the financial parameters page. So we can see debt payments happening here for the 18 years. And there's some variation in those payments because we're using a sculpted debt method, so that the debt payments vary with the cash available on hand. And then at the end of the debt period, we start earning some revenue, but then we have these negative years where there are battery replacements. So that net present value is capturing all of those elements of the cash flow. So if we want to verify what the battery is doing, a quick way to do that is to look at the state of charge of the battery over the year. And one way to do that is to look at the heat map tab on the results page. This is showing me a list of all of the time series output variables from our simulation. And we're just going to focus on the battery state of charge. So I'll filter the list and choose the battery state of charge. And so what this snapshot is showing me is the entire year in one handy graph. The x-axis is going from January to December, and the y-axis is going from midnight to midnight. So we've got noon here at the middle of the graph. And so each vertical line here represents a single day of the year. And what we can see is that the battery, and the colors here are the battery state of charge. So red or dark red is fully charged and blue is fully discharged. So the battery is discharged at night, and then as the sun rises in the morning, the PV array charges the battery, and throughout the year it gets fully charged sometime around noon, and it stays fully charged until 4 p.m., which is when our manual dispatch schedule says we can start discharging the batteries, and it discharges over a period of 4 hours based on the capacity of the battery. So this graph just confirms that the battery is doing what I expected. So I want to see what I can do to try to increase the net present value, see if I can get a positive net present value. And to do that, I'm going to try, sorry here, just, I'm going to try a bigger battery. Maybe if I have a bigger battery that can discharge over a longer period, I can sell power over a longer period and increase my revenue and therefore increase my net present value. So let's just try doubling the size of the battery and leaving everything else as it is. So I run a simulation, and that actually made my net present value worse. And that's because I increased the upfront cost of the system, and I also increased these replacement costs by making the battery bigger, but I did not increase my revenue by enough to cover those additional costs. And I can just take a quick peek at my heat map and make sure that the battery is indeed discharging over a longer period because of that increase in capacity. All right, so increasing the size of the battery was not helpful. I'll go back to my default 4 kilowatt-hour battery and try some other things. My dispatch schedule here says to discharge at night, so I'm storing the PV power during the day and discharging it at night. If we take a look at my power price, it's just a fixed price. So I'm paying $7 per kilowatt hour, regardless of the time of day or time of year. So I'm going to try adding a time of delivery multiplier here. So what I'm going to do is increase the PPA price at night when I'm discharging my battery to see if that helps move my NPV up above 0. And so I'll define a new TOD, time of delivery period. Period 2 will have a multiplier of 1.5. And then I'm going to define period 2 as being from 4 to 11 p.m. So I just draw a rectangle in this matrix, type the number 2, and do the same for the weekend to make it the same. So this is matching my dispatch schedule on the battery storage page. And so what this means is that from 4 to 11 p.m., I'm going to get 7 cents times 1.5. So I think that's 10.5 cents per kilowatt hour for any power that I deliver to the grid at night. So let's run a simulation now and see what happens. Okay, back to just discharging my battery to 4 hours. Look at the summary page and see that the net present value is negative 1.7. So we're getting closer to 0, but it's still negative. The next thing I want to look at is the price that I'm paying to charge the battery. So that's determined on the electricity rates page. And here it's set to no electricity rate. So what this means is that the power used to charge the battery is being treated as negative revenue. So basically we're paying the same price to sell power and to buy power. If I choose this enable electricity rate option, now I can define a different price for electricity purchases. And I also will be considering electricity purchases to charge the battery as a project operating cost. So the basic assumption here is that we're paying retail rates for power to charge the battery, and that goes into the cash flow as an operating cost. So we can make the structure for these buy rates as complicated or as simple as we want. I'm just going to stick to a simple flat rate, and I'm going to be generous and make it 5 cents per kilowatt hour. So we're selling power at our PPA price with that PPA multiplier, and we're buying it at this 5 cents per kilowatt hour retail rate. So if I run a simulation, and look at my net present value, it did not make much of a difference. If I check my cash flow tab here, so now the cash flow tab shows me the cash flow detail that's used to calculate that after-tax cash flow. Sometimes the scroll bar doesn't appear in the cash flow, but if you minimize and maximize the window, it reappears. What I wanted to show here is that under operating expenses, we have this electricity purchase item. So this is showing the cost of buying electricity to charge the battery, and that's considered one of the tax-deductible operating expenses. And we can also, by the way, see the battery replacement costs here happening in years 8 and 15, based on how the battery is being cycled. So I'm still not getting a positive net present value. So one last thing I want to try to see if I can get the net present value to be positive is to maybe try a smaller battery. Maybe I just, that the cost of the battery is too high for this large battery. So I could run a few more simulations trying different battery sizes, but I wanted to show you a trick that we call parametrics. So under the simulate button here is this parametrics button. And what parametrics allows you to do is to assign a range of values to an input variable. So in this case, we want to assign a range of values to the battery capacity. So I'll click quick setup here to set up my range of variables, and then I'll click add to add a variable, and this gives me a list of all the input variables available in the case, and there are a very large number of them. So I'll sort it. I know I'm looking for a variable that has capacity in the name, and there it is under battery sizing, desired bank capacity. So I'll check that variable name, and there's our 4,000 kilowatt hour value that we set on the battery storage page. I'm going to either click edit or double click this number to assign a range of values. So let's go small. We'll start with 500 kilowatt hours all the way up to 4,000 kilowatt hours in increments of 500. Click update, and there's my range of values. So I'll click OK to get out of all these windows. And that created a table here of battery bank sizes. And now we need to choose an output. We're using net present value, so I'll add net present value. This is a list of all the output variables available for the case. And I'll find the net present value metric. And now I'll run simulation. So I'll use this run simulation button up here. And now it's running my front of meter battery model for each of those battery capacities. And what I see is that I can get a positive net present value for if the battery is smaller than somewhere between 2,000 and 1,500 kilowatt hours. And with a 500 kilowatt hour battery, I get a net present value of $737,000, which is higher than my PV only system of 600,000. So it looks like if I add this smaller battery, I can get a little more revenue out of my PV system. And then if I wanted to explore that in more detail, I would go back to the battery storage page, set the capacity to 500 kilowatt hours, and run a simulation. And then I can explore all the detail in the cash flow and the time series and so on. Okay, so that's the manual dispatch. Are there any questions about manual dispatch before I carry on to the automated dispatch options?
Hi, Paul. I don't think there's any remaining questions.
Great. All right. So let's look at the automated dispatch. I'll go back to my slides here if I can find them. Okay, so unlike the manual dispatch where we told SAM when to charge and discharge the battery, the automated dispatch options in SAM are SAM determines when to charge and discharge the battery based on a number of considerations. So this is a decision that SAM makes in each time step. The time steps can be hourly, or if you have sub-hourly weather data, you could make run the model in 15-minute, 10-minute, even up to 1-minute increments. And so in each time steps, SAM has to decide whether to charge from the grid, charge from the system, or discharge to the grid. There's a nice detailed article that describes the automated dispatch algorithm that I provided a reference to here. You can find a link to it on the SAM website. So the basic rules for automatic dispatch are that if we have a special case of a PV with a battery that's connected on the DC side of the inverter, that we're always going to charge the system when the array power exceeds the inverter power. So that's to avoid inverter power limiting. So if you have an array with a high DC-AC ratio, whenever the inverter would limit the power, you can send that power to the battery and store it to use later. For otherwise, SAM's going to charge this from the system if it thinks that it's going to be able to sell the power later. So that's going to be depend on what forecasting method it uses. And then it will always charge from the grid if the purchase price in the current time step is less than the predicted future power price. And then if it's in a high power price period, then it will discharge to the grid. And the goal here is to dispatch to maximize revenue. So it's considering the value of electricity sold to the grid, which is determined by the power price. That could be that PPA price or market price. It's considering the cost of electricity to charge the battery. And as we saw, that could either be the PPA price or a retail purchase price. And then an additional consideration is a cost of cycling the battery. So it's going to avoid overcycling the battery if it results in too many replacements. We want to minimize the number of battery replacements. Okay, so let's switch back over to SAM and oops, have a look at the automated dispatch. So for this, I'm going to create a new project. And we're going to choose battery storage. We're sticking with detail PV and single owner. And so this is the default PV single owner case, and it's very similar to the one we've been looking at. It's in Phoenix. It has a 20 megawatt array, this 4 kilowatt hour battery, and it has a higher PPA price than we were looking at before, 9 cents per kilowatt hour, and with this multiplier in the evening. So I'll just stick to this default system and run a simulation. And I guess I forgot to mention that default case is uses the manual dispatch. So it's similar to what we were looking at before. And if we look at a heat map of the state of charge, we'll see the battery charging during the day and discharging in the evening, like we saw before. So now let's change that to automated dispatch. So we've got a few different dispatch options here. I'm going to choose the automated look ahead option, which this is going to make the dispatch decisions based on the solar resource and the power price over the next 18 hours. You can change this to 24 hours or 12 hours. But you might consider it to be a perfect forecast because it's looking ahead to see what the weather data is and what the power price is, and it makes a decision based on what the future is. So let's run a simulation and see how SAM dispatches the battery. So I'm looking at my heat map here of state of charge, and it looks like it discharged at the beginning of the year from its, I think it starts off at 50% charge, and then it never charges it again. So that's no good. That's not a very good automatic discharge algorithm. Why is it doing that? Well, when you choose the switch over from manual dispatch and go to automated dispatch, you'll notice there's a couple of inputs that are activated. In addition to the dispatch frequency inputs that I showed you, there's this battery cycle cost. And it's by default set to calculate automatically. So let's investigate this a little bit. If I go back to my results and go to data tables and cycle cost, there's this battery computed cost to cycle. If I click that, I see that there's this cost is 6 cents per time step, per cycle in each time step. So what this is a penalty that SAM has calculated based on our battery replacement cost. That says it's gonna penalize the algorithm using this 6 cents value to minimize cycling the battery, to minimize over cycling the battery and lengthen the life of the battery. So what this is basically telling us is that the replacement cost, given the high replacement cost for this battery, it doesn't make sense to cycle it, and given also the PPA price and the cost to charge the battery. So we can investigate this further by entering the cost manually, and just if we try lowering this cost, we should get to a point where the battery, where SAM will dispatch the battery. So I'll try changing it from the calculated value was 6. I change it to 5 cents. So there's this time it's the value that I entered, and let's see if we still don't have any battery discharging. Let's go down to 3. So there, now the battery is discharging. So I've artificially, I overrode SAM's automatic calculation of the cycle cost that's based on what it predicts the cost of replacing the battery will be based on our inputs to demonstrate that how this battery cycle cost input works. But I don't want to artificially lower that cost. So I'm going to go back to calculating it automatically and see if there's some other way I can get the battery to dispatch. So we can try the methods we use for the manual dispatch. We can change the battery capacity. We can change the electricity rates, and we can change the PPA price. And so what I'm going to do here is give us a more interesting PPA price multiplier schedule. So this is a generic schedule that we provide as an example. It has this summer peak here, period 1, that has a very high multiplier. So it more than doubles the PPA price. And then we have a pretty nice multiplier here in period 2. So during the summer daytimes, we have the high multipliers and a pretty nice one too. So throughout the whole summer, we're incentivized to sell power during these high multiplier periods. So I'll apply this TOD multiplier schedule to the PPA price and run a simulation and see if that results in the battery being used, and we can see that it does. And during the June to September months when we have those high PPA multipliers, SAM is dispatching the battery. And we can check our net present value and see that it's still positive, so seems to be financially reasonable. And if we want to look in more detail to see what's happening, we can go to the time series tab where we can look at how the battery is being charged and discharged in more detail. So I'll look at electricity to battery from system and electricity to grid from battery. And let's zoom in here to last few days of June, first few days of July. Okay, so we can see that the battery is charged. This blue line means the battery is charging, and the orange line means the battery is discharging to the grid. And I'm going to add a couple of other variables here. The GHI, so this is the solar irradiance. I'll put it down on the bottom graph by clicking the right box there. And then let's look at those TOD multipliers. Okay, so the solar irradiance here is in red and the TOD multiplier is in dark gray. And this is just the data from here. So we can see that 2.0 whatever multiplier is here, and then their 1.2 multiplier. And so if we kind of move through the day here, we can see that, and this appears to be a weekend because those high multipliers don't apply on the weekends. So we can see that Sam's going along here and saying, oh, I have a high PPA period coming up in the next 18 hours, so I'm going to charge the battery. And then during that high power price period, it discharges the battery. Okay, and so it does that in for each day. Okay, now let's compare that to the look behind option. Whoops, this is the look ahead option. So I'm going to just rename this case, and I'm going to make a copy of this case. So case and then duplicate. And I'll rename this look behind. And so this is a copy of this case. I'm going to change one thing. I'll go to the battery storage page and choose the look behind option. So here, Sam is going to, instead of dispatching based on what's happening in the future, it's going to dispatch based on what happened in the past. And the only reason to do that is just to make the forecast a little less accurate, to make it a little bit more realistic. Because in real life, you're not going to be able to fully predict what the solar resource is doing, or perhaps in market price situation, what the prices are going to be doing. So this adds a little uncertainty to your dispatch predictions. So we'll run a simulation. And let's try looking at those same variables. So battery, electricity to battery from system, and then electricity to grid from battery. And we're going to zoom in here to, what is it? June 29th to July 3rd. So June 29th to July 3rd. And then let's look at the GHI and the TOD factors. And if we compare these two, we'll see that the dispatch is a little different. So in the look behind scenario, it's dispatched here on the weekend, even though that PPA multiplier didn't apply on the weekend, because it charged in anticipation of yesterday's PPA price, high PPA price multiplier, and then shouldn't dispatch because there's the PPA price wasn't higher. So that's why you see a different dispatch pattern for the look ahead and look behind. Now there's another option for the automated dispatch, which is to use a custom weather file. So this is yet another way to add some uncertainty to the forecast. So instead of using the weather file from the location and resource page that's used to calculate the PV array's output, you can choose a different weather file. So you're going to dispatch the battery to a different weather file so that the battery dispatch doesn't exactly match the PV output. And so you might use a weather file for a different year if you're using single year weather data, or you might use a weather file for a different time zone if you want to shift the battery dispatch ahead or behind. So that's a quick summary of the 3 automated dispatch options. Any questions about those before I move on?
Hi, Paul. I think all the questions, we don't have too many questions right now. I think they can wait till the general Q&A.
Thank you. Thanks, Matt. The last thing I want to show you on the dispatch options is this dispatch to custom time series. So this is not an automated dispatch option. It's, I guess you could call it a manual dispatch option. This is, in this option, when you click this radio button, this button down here gets enabled. And what you do is you just tell SAM on a time series, on an hour by hour basis or sub-hourly basis if you're running sub-hourly simulations, you just tell SAM exactly how you want to charge and discharge the battery. So this is useful if you may have an external battery dispatch model that's generating time series data, and you want to run the battery model in SAM according to that dispatch schedule. And I'll just show you quickly how that works. So you need to provide a row of dispatch values for each hour of the year in this case. So there's 8760 hours in the year, and a negative number means you want the battery to charge, and a positive means you want it to discharge. So let's say we want to charge our battery at night, and it's that 1000 kilowatt maximum charge rate. So I'm going to charge it for 4 hours at 250 kilowatts, and then I want to discharge it during the day, let's say 100, something like that. Okay, and then of course I'd have to provide it for the whole year, but since I'm doing it by hand, I'm just going to do it for the first few hours. And then if I run a simulation and clear these out, let's look at the battery, electricity to and from battery. And I don't need my solar resource. Don't need these guys. And we're going to go to the beginning of the year. Okay, so it looks like we're discharging during the day, but not charging at night. What's going on there? Let's go back and have a look. I'm saying the battery can charge from the system, so there's no way it can charge at night from the PV array. That's why it didn't charge in spite of the fact that I asked it to. So I'll let it charge from the grid. And now I can see it charging and discharging. I could also look at this data here. And let's see. Yeah, so it seems to be working as intended. If the battery state of charge, it'll only discharge the battery if there's capacity available in the battery. So if this battery state of charge goes below the lower limit, then it's not going to discharge. So that's the time series dispatch. Okay, so since I messed up at the beginning and had to start again, I think we'll go over by the amount of time that I delayed at the beginning. So make sure we have time for questions. So hopefully you guys can hang out a little past the top of the hour. But I should be able to finish the material I wanted to cover before then. The DC connected versus AC connected, I'll just touch briefly on this. So this is for PV systems only. The generic battery system assumes that the battery is AC connected. So this DC connected option is only available with the PV battery model. And the AC connected battery, which is shown down up on this top diagram that I took from that DREO article that I referenced earlier, just shows that the battery has its own bidirectional inverter. It interacts, it's connected to the grid interconnection point, and the PV inverter is connected as well. And so the battery can interact with the grid on its own, independent of the PV array. So this is sort of common if you're adding storage to an existing PV system, and it's fairly simple. The dispatch is simpler to manage because you're not interacting with the PV array. But a more sophisticated system, maybe if you're designing it from the ground up, it would be a PV battery system where the battery is connected on the DC side, and that way you can experiment with higher DC AC ratios where you shift that power to the battery when the PV array output is higher than the inverter capacity. It does require some more sophisticated controls to dispatch the battery in response to the PV. The article that I mentioned has a discussion of the trade-offs between AC and DC connected if you're interested in exploring that further. I can show just quickly how that works here. So we have our PV battery case, and I'll switch it over to DC connected. And then when I do that, I have a new option, which is battery can charge from clipped system power. So let me just turn that off for a second. And this array has a DC-AC ratio of 1.18. And I'll run the simulation. And one way to look at the clipped power is, let's see, this AC inverter power clipping loss. So this is not really a clipping loss, it's power limiting loss. But we can see that it's fairly small. So let's increase the DC-AC ratio of the system. I'll just add more strings to give us a DC-AC ratio of 1.43. So now we're clipping loss of about 3, or power limiting loss of about 3% per year. So that's getting to be significant. If we go back to battery storage page and allow the battery to be charged from clip system power, so that brought that loss down to 1.75%. And of course, you could experiment with different sizes of battery and different dispatch options and so on to optimize the design of that system. Make sure your net present value is positive. And then the last couple things I wanted to discuss is the generic system battery is useful for modeling battery-only systems. We don't have a standalone battery model in SAM at the moment. We're working on one, so keep your eyes out for that in a future version of SAM. And then the generic system battery model also provides kind of a workaround to model, for example, a wind battery model system, because we don't have a wind battery model in SAM. So let's take a look at the generic system battery single owner. So this generic system model is designed to be a basic model of a thermal power plant of some sort. So it has a heat rate and a capacity factor. And on the system cost page, it has cost for fuel. But you can just ignore the fuel costs and use it for other things. So one thing is, if you wanted to model a battery only system, you could set this capacity factor to 0, and that would effectively remove the power plant from the simulation, and then you'd have a battery only system that interacts with the grid. I think in some other webinars we've recommended setting the nameplate capacity to 0. It turns out that causes some calculation errors. So we want to set the capacity factor to 0, not the nameplate capacity. And then the other thing we can do with the generic plant is import a generation profile from a different model. So you could set up a wind model in SAM, run a simulation, export the generation profile from the wind model into here. So you'd export the generation profile from your wind case to a text file, and then click import to import the generation profile here. And then the battery would interact with this generation profile. And then the last thing to mention is the merchant plant financial model. So this allows you to enter the power price as a time series. And so it's rather than a fixed price with a set of multipliers. And there's also a capacity requirement. And this makes the merchant plant a little tricky to work with PV and storage, which may have negative power at certain time steps. Because the simulation will fail if the capacity requirement is not met in any time step. And that's because the assumption is that would violate the terms of the contract. You have to meet the capacity requirement. So I'll just show you quickly how to set that up. So you can click add a case here. You do detail PV and then merchant plant. And this merchant plant model involves lots of calculations because it has to run the simulation over the entire analysis period, and that has power prices for each time step. So those power prices are defined on the revenue page. And you click edit lifetime data and you provide your market prices here, and then the cleared capacity in this column. So well, I don't have time to go into a lot of detail about that, but I just wanted to point out that it is an option. If you're working with a merchant plant model and have questions, please get in touch with us and we can help you out with it. So that's what I had for presentation. Are there any questions?
Hi, Paul. Thank you for the great presentation. I'll give people a minute to type, but we did have one that we wanted to see if you had any comments on. The question was regarding wholesale or value of solar pricing. Basically, do you have any comments on applications where retail pricing isn't applicable? And that's from James Orenstein.
Thanks, Matt, yeah, and James for the question. I don't have a lot of insight into that question. I know that it's that developers are looking at both scenarios. But I'm not a great person to ask about what's actually happening out there in the world because my head is buried in the modeling aspect of things. So sorry, I don't have a whole lot of insight on that.
There's nothing else that's popped up yet. People might still be typing.
Okay. And while we're waiting, I might just point out the SAM website here. You can sign up to post questions on the forum if you have questions that we don't get to today. And then you can find links to the various videos by looking at the videos pages. So here's our battery storage videos. And we have photovoltaic videos. And then the events page is where you can find links to this year's webinars all in one place and registration for the next one. All right, well, we can wait another couple minutes to see if there's any other questions, but
I have one, Paul, that just came in from Hillary Sewell. What is an example scenario of when charging from the grid would be beneficial?
well, I think if you have time of these time of delivery pricing, let's see, you could it could be that there's some time when there are very low power prices. So let's see, that would be on this revenue page. You know, if you have a period where, you know, like period 6 here, where the power price is 70% of the nominal PPA price, it might, and then you have this period where it's twice, so it might be worth storing, purchasing from the grid during this low price period and then selling it during the high price period. But that would depend on your project economics, of course, whether that was actually profitable.
Okay, thank you for that, Paul. And then she just had a follow-up. The red areas are reflecting not discharging, correct?
So yeah, sorry, we have, there's 2 different places where we use these schedule matrices. So this is on the revenue page. And so we have a PPA price of 9 cents per kilowatt hour here, which we can change. And then these multipliers apply to this PPA price. So that means that during period 1 here, the PPA price is going to be 0.09 times 2.064. So it's going to be about 18 cents per kilowatt hour here. And then in period 6, which is this red period, that the power price is going to be 0.7 times 0.09. And then on the battery storage page, if you're using the manual dispatch option, you have the dispatch schedule here. And this is what controls the battery, how the battery is dispatched. So if you wanted to use the same schedule for the TOD pricing multipliers as for dispatch, you can click this copy schedules from TOD schedules. And that just copied those matrices, so you can get the periods to line up, your dispatch periods to line up with your revenue periods. So yeah, there's 2 different schedules. Of course, if you're using automated dispatch, then this schedule doesn't apply, and SAM is going to automatically dispatch based on the power price determined by this table.
Okay, thank you, Paul. There's a clarification question. It looks like you said to add some uncertainty, you suggested to change the weather file to a different year or time zone. I want a clarification on what you meant by time zone. Do you mean to change to a different city or area?
Yeah, that's just a suggestion. If you wanted, if you use a weather file for a different city that's in a different time zone, then the sun is going to rise at different times than the PV output, and so then the battery dispatch is going to respond to a completely different solar resource than the PV array. So that would add, significant uncertainty to that part of the dispatch algorithm.
Okay, thank you. I think that's it on questions.
Okay. Great. Well, thank you everyone for participating in today's webinar. If you have other questions, please get in touch with us on the forum. And I hope to see you at another webinar. We'll post a recording of this webinar by the end of the week, along with a transcript of the Q&A. So that's all for now. Thank you very much. Have a great rest of your day. Goodbye.